Cool. Yes, I'm David Miloschewsky. This is joint work with my advisor, Supartha Podder, which we titled New Lower Bounds for Quantum Computation with Non-Collapsing Measurements. Now, again, as we've already said several times, a bunch of people here don't like quantum computing that much, but I'm still going to go over it because it's kind of a baked in part of this paper. And I'll try to give you all the necessary background that you would need just to make it a little bit more accessible. So yeah, specifically, I think we're all familiar with classical strings. You know, classical string can simply describe the memory that we have at some point. And if we switch to the quantum setting, the classical string becomes a quantum state, which is just a superposition over multiple classical strings. But again, we're inherently classical beings. We're not quantum beings, so we cannot directly access a quantum state and read off of it exactly without some prior knowledge. And so if we want to, let's say, sample it, we have to collapse it or measure the state and turn it back into a classical state, classical string. And this kind of reminds me of the phrase, you cannot eat your cake and have it too, where the cake is our quantum state in a superposition. And if we want to actually process it, or we have to collapse it and turn it into a classical string that we can process in our stomachs. So, with this dichotomy in mind, we can try to describe the model that we're going to be working with, which is the quantum circuit model. Here, one is given some input x, and you run some transformation to your input, and you can, again, collapse part of your quantum state, and you get some, let's say, state psi1, and you continue on, or applying more unitaries and more collapsing measurements, so on. Now we can get into the part of the title that says non-collapsing measurements. For those who are, even for those people who are actually interested in quantum, you might not be sure what that is. Essentially, going back to our phrase, it's asking, what if we could eat our cake and still keep it? So specifically, what if we could take our quantum superposition, we could get a classical sample, some classical string, but we could still keep it in a superposition. So it wouldn't collapse into the classical string that we still receive. And so if we look at the quantum circuit model, we would basically be taking this top part would be the same, except after like each round of some actions, some unitaries, it would split into two parts. One would be the quantum state that would be continuing its computation, and the other one would be some measurement, which would collapse to some string S1. And with, again, more steps, you get more samples from this computation. Now, what is interesting about this model is that if I was only able to perform these non-collapsing measurements, and I can actually perform collapsing measurements, then you could simulate this directly by just running parallel computation multiple times and just performing a measurement at the end. However, if you kind of combine the two, combine these non-collapsing measurements and actual standard collapsing measurements, then you get something that's just a little bit more powerful, as I'm going to explain. Yeah. Now, if we try to look at this model of computation in the complexity zoo, it would be labeled using the label PDQP, which stands for product dynamical quantum computing, which, yeah, you don't have to really look into that name too much. But what is interesting about it is that as opposed to BQP, standard quantum polynomial time without an error, it's a little bit stronger than it. And unlike BQP, which is within PP, the tightest upper bound we have is the counting hierarchy, or more specifically, BPP with a PP oracle. And so it means that like we're actually getting some notable power with this model. And furthermore, it's actually, this model contains the statistical zero knowledge, which BQP does not. So somewhat by studying this model, we can actually try to study the relationship between these classes in a new, different way. Yeah, and also I just want to say, like, does anyone have any questions about the model? I kind of want everyone to understand what I'm talking about. Yeah, go ahead. Like these? No. So the way it would like work precisely is that you describe your quantum circuit, and like as a Turing machine, you give it to some oracle that gives you those samples back, and you process them and then make your decision.
Is this like physically motivated? This system?
No, this is like fantasy quantum mechanics. So this is the point of this is more for complexity theoretic reasons, and I guess somewhat the motivation might actually be like, okay, this is maybe why this is not true in for quantum mechanics, because we actually get some results that we don't believe to hold. Okay. But yeah, so this is going to be the query model that we're going to be studying, where instead of having some input X, you actually access it through some unitary gate Q. And in these models, standardly, what people measure are the number of queries Q or number of unitary Qs that you're running. However, if this was the only thing we cared about, every problem could be trivially solved using one query. Because you could make a query in superposition, you'd have all the inputs at once, and you could just perform non-collapsing measurements on those. So you could be sampling that superposition over and over. And you would be bound to just learn the entire function eventually. So if you want to study the query complexity of this, you also have to consider the number of these non-collapsing measurements that you're actually performing. And so in the original paper, which introduced this class, the authors showed that if you're trying to address the query complexity of both Q, number of queries, and P, the number of non-collapsing measurements, the query complexity of solving unstructured search, so just deciding if there's a bit that's 1 or all of them are 0, is somewhere between n to 1/3 and 1/4. And this means that we actually have an oracle separation with NP, which can trivially solve the problem. But, and this is a difference between BQP and PDQP, non-collapsing measurements allow us to solve the collision problem using a constant number of queries. Specifically, the collision problem is the problem where you're given access to a function, and you have to decide if it's 1-to-1 or if it's 2-to-1. So if for each output you have one input towards it or two inputs mapped towards the output. And in this promise, given this promise, you can just query all those inputs in superposition. Then you collapse the output register to some output, and you can repeatedly perform non-collapsing measurements on the input register to decide if there's one input or two different inputs. And so this is a summary of basically our lower bounding results. So just a note, here's a column with BQP results just as a comparison. And the collision problem requires n to 1/3 queries but in BQP, but in the PDQP model, it's a constant number of queries. So here are our results. Now, basically all of the first, second, and fourth row are either improvements or just new results that we got. And here, this column is essentially taking the non-collapsing measurement model, but we added a restriction, asking ourselves, what if we actually only allowed non-adaptive queries? How much would that hamper the speed up that you would be getting? And the answer is just a little bit. So to kind of go over the results in more depth, we tightened the search lower bound to n to the 1/3 for PDQP. And then for majority, we showed that it's square root of n in both adaptive and non-adaptive cases. And then interestingly, for the element distinctness problem, which is a relaxation of the collision problem, which is essentially just asking if a function you're given is one-to-one, or there exists at least one output which has two inputs mapping to it. Here, the query complexity, again, becomes polynomial as is standard in quantum computation. And this is interesting because for BQP, you can get the relationship between the two problems somewhat directly. Like the algorithm for element distinctness can also be used for collision and vice versa, but that doesn't hold for in this new setting. Right. So let's just kind of explain the proof technique. Essentially, yeah, it's in summary, the proof technique is using the quantum adversary lower bounding method and applying it for our for this model of computation. So specifically in the adversary method, the goal is to come up with some progress measure of an algorithm and show that in order to solve this problem, some problem efficiently, the progress measure has to make, let's say, t many steps. Specifically, suppose that these would be two states at the end of an algorithm, psi x and psi y, such that their outputs are different. So if we're at the end of the algorithm, then we require the inner product to not be one, be strictly less than one, so that we have a high chance of distinguishing, of like obtaining the right answer when we collapse these states. And you can generalize that to just any state. And instead of using inner product, we use fidelity, which is just a generalization of the inner product. So we can define some relation of inputs, x and y, where x and y always have different outputs, and sum over the fidelities of the outputs at, let's say, step t. And this sum would be our progress measure after performing t steps in our algorithm. And with this, we just kind of directly get that at the start, we're just kind of everything, all these fidelities are one. So we're just summing over the relation, and we require this to kind of go down by a constant. And so in the proof, what kind of remains to be shown is just, okay, what is the effect of some unitary or some measurement or some query operation on the fidelity of these states? Now, this is somewhat hard because this query model that I showed before, it's a little bit, it doesn't really allow us to do that. So we generalize it and essentially turn it into using parallel copies. So earlier, as I mentioned that if you didn't use partial measurements in your quantum computation, you could actually simulate the non-collapsing measurements by running them over and over. But again, we need those collapsing measurements to essentially actually get the additional power. So what do? We come up with a new measurement gate, which runs, let's say, L copies at once, given that we made L non-collapsing measurements. And whenever we perform a partial measurement on one of them, we ensure that the same partial measurement occurs for all of the copies. So at each step, each of these registers is exactly the same as the register above or below. And then at the end, these are the outputs that you'd be actually getting from your non-collapsing measurement model that you'd be feeding to the Turing machine. Yeah, and so basically what we can then show is that the application of unitary transformations, these used, they don't affect the fidelity measure at all. So if you have two states and you apply it to them, fidelity remains the same. And what we show is that this new measurement gate that we came up with does not decrease fidelity. Therefore, applying it cannot actually improve the progress the algorithm makes. And then, so all that remains is considering how applying the Q unitaries changes when you have this parallel model. But using the fact that these are all the same copies, we're actually able to show that it doesn't differ by much from just having basically one line of computation. Yes. Any questions so far? Okay. And this kind of concludes like the part of the talk on non-collapsing measurements. And then we also realized that our technique translates well to a different type of model. So coming back to our cake question, suppose that instead of having, let's say, instead of eating your cake and having it, you could just double the amount of cake you have. So that basically means, in the quantum sense, that you could copy your state that you'd be holding. And somewhat directly, you can show that if you're able to copy or clone, you can perform non-collapsing measurements because you can always clone and then immediately measure one of the states. But this model is actually much stronger than PDQP, as there's a result that shows that search can be solved using logarithmically many queries or copies. And we show that this is actually tight, basically by using the same proof technique as above, but just without the assumption that each register is exactly the same, and instead the unitaries can basically map them elsewhere. And yeah, and so then kind of getting back to some open questions, I think one interesting open question would be kind of looking for other classes that are somewhat sitting somewhere just above BQP, because all the other metaphysical classes like post BQP that was mentioned before or other ones, they actually sit way above PP and encompass a lot of like very strong classes. And then furthermore, can we come up with some new lower bounding techniques that either for standard quantum computation or just these metaphysical models? And lastly, can we find some hard problems for CBQP, because this class is actually equal to BPP to PP. And so if we could find some problems that are hard for it, we could actually we could try to aim for oracle separation between the class and P space, which would be the closest class we would know to P space to have an oracle separation. Yeah. And then lastly, I wanted to do a little shameless plug. So I've been working on a project called the Complexity Garden, which is essentially a visualization of of these types of spiders, which you can basically show off, look at different complexity classes. So is it okay if I just show a link? Yeah. So for example, let's say that I do want to learn about PDQP, then I can just look it up. And by kind of looking at it, I'd be like, okay, which classes are around PDQP? I could expand the classes around a little bit and find that it's between, let's say, that it's below the counting hierarchy and it contains SEK and BQP. Or let's say that I was interested in P and P space and wanted to know what are all the classes between, then I could just like expand this to learn all about those. Yeah, all about these. So yeah, this is just like a little pet project that I'm working on, and yeah, I'd appreciate any feedback or suggestions. So thank you very much.